do yet, but my boss wants the first input into it now, so I've been working on it, but it's not there yet. So in other words, Thursday I had no time at all to get ready for this week, so that's why I came in early today to get my physics labs and tests run off for this afternoon, but it took me a while to find everything and put all the pieces together. So I think we are recording. Enough of my sad, sad music. So let's get going. And of course, the first thing I want to ask as soon as this does come up is, do you have any questions for anything we've covered so far? If not, let's continue with where we left off before. I believe it was example 4. Okay. Pretty easy example. Has nothing to do with that line to speak of, so, whoa, let me get my pen color changed. Okay. Find the derivative of f of x is equal to 9x minus 5. I can't read. Okay. At x equal 2 and x equal 5. Okay? We want to know the derivative of that. Now, just a little bit of review and reflection here. There was the last thing we did. I'll emphasize this again. Blowing it up. Okay. If f of x is what kind of function? Oh yeah, there it is. Linear function. What is the derivative? The slope of that linear function. If f of x is a continuous function, or I mean a constant function, what is its derivative? 0, because the slope of a constant function is 0. There is no m. M is 0 there. Okay? That said, what kind of function is this? Linear. So what is its derivative? What we were using before, f prime, yeah. F prime of x is equal to what? 9. So what is f prime at when x is equal to 2? That's not 9x. It's f prime of x anywhere. The x, whatever x value is 9. So what is f prime of 2? 9. Okay. And what is f prime of 5? 9. Okay, very good. The derivative of a constant function, of a linear function, is the constant slope. Whatever that slope is, that's the derivative everywhere. Okay, if you remember back this figure here, I'll blow it up too. This isn't the same one we had, but it is a linear function, and I think it's the one we looked at before. Whatever the slope is here, the derivative of m, that's the slope here, and 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 here. Everywhere, the slope is that value m. Make sense? Okay. All right. Let's do example 5. Okay? Determine the derivative of the function f whose graph appears in figure 8 at x equal 2, 3, and 4. Please show figure. No. There it is. No. They aren't showing it. Boo hiss. what's the last one we did? Okay. So it looks like I'm going to have to kind of draw it. Do all of you have books or some way you can look at that figure? Okay, if not, could you look on with somebody else that close by who has? Okay. And we want to determine the derivative of the function f, whose graph appears in your book, okay? And by the way, make sure you're looking at the right graph. This one right here. It's figure 8 in the new text. Obviously, the old edition didn't have this figure in it, or else they didn't put it in the slide set. So everybody see it? Found it? Can you look on with someone who has it if you don't have it? And what we're asked to do is to determine the derivative of the function whose graph appears there. I swear I still can't do it without. So let me I hope this isn't, yeah, that does okay. I'm going to, it's going to take a while for this to open. Sorry, I didn't realize this figure wasn't on the slide set. This is it's open right away. Good for it. Okay. Open at current slide. Okay, let me try to draw this thing. You give me some points to put in here. One, one, is that what I heard? If I can get my pen to work. Okay, 1, 1. Okay, let's see, we're going up to 5. Yeah, okay, 1, 1 is there. Any others? 2, 2. Any others? 3, 3. Y'all are good. Okay. Any others? 0, 0. Okay, I wonder when someone's going to do the hard one. Any others? Come on now. 4, 1. Okay. Did everybody see that? Okay. Here is the graph of that function. Okay. Now this is the part I don't like. Let's do 5, 1/2. Get out of there. Okay. Something like that. And I will try to give it a curve like that. Okay, we don't know where else it's going. Okay. Now, it asks for you to determine the derivative just looking at the graph, well, basically, at x equal 2. What's the derivative there? Anyone want to hazard a guess? 1, absolutely. F prime of 2 is equal to 1. Why do you say that? Yeah, the slope of that line, that's a 1-to-1 slope. Y is equal to x, the slope is 1. So at 2 is 1. How about at 1? It's 1 also. Okay. Now, they also do another thing here, and I'm going to do it the way they did. They show a tangent line at x equal 4. And the tangent line at x equal 4 is that one there. Obviously, my drawing leaves a little to be desired. So let me see if I can pick up on that and do a little bit better at it. Sorry, this takes so long to get the right color and everything else. Something like that. It's a little closer to theirs. All right. Let's jump over to the derivative of this function at x equal 4. F prime of 4. Anyone want to hazard a guess there? -1, because this, if indeed that is a tangent line, which we assume it is, it kind of looks like it in the book, it's even more so, the slope of that tangent line, which is a derivative, first derivative, is going down 1 for every 1 to the right, so that's a -1. So f prime of 4 is equal to -1. Very good. Now let's do f prime of 3. What say you? I chose to do them out of order. What's the derivative of f at 3? I'm sorry? Does not exist. Why? Because the left-hand limit is 1, and the right-hand limit is something negative. Near the twain do meet, I mean, they meet there, but it's a continuous function, but the derivatives are not continuous. Okay? So yes, that one does not exist. Now, how do they say it? At x equal e, there is no well-defined tangent line, since the limit of the slope secant line as x approaches 3 from the left is different from the limit of the slopes of the secant line as x approaches 3 from the right. So therefore, you're absolutely right, f prime of 3 does not exist. Okay? And you got the other two. Very good. Now, let's I really wanted that to just go away, but oh, there it is. Okay, let's get this one. Yeah. Back. Current slide. Okay. We're coming back to this slide in just a second, I think. All right. This is the figure that we're going to deal with, and remind me to go back one slide to get the verbiage for this. Okay. When h is a very small number, remember our definition for derivative is the limit as h approaches 0 of f of a plus h minus f of a over h. Okay? F of x plus a, yeah. Whatever you want to call this, the thing. And if this h is small, meaning these things are pretty close together, then the secant line, the secant line isn't quite the tangent line, the slope of the secant line is not quite the same, but the closer h gets to a, I mean, the smaller h is, the closer a plus h is to a, then the closer and closer that secant line is to being the slope of the tangent line. So when h is small, the secant line has nearly the same slope as the tangent line, right? Now let's translate that into something else. Let's go back here and say this. Notice what's missing from this. This is an approximate equal. For that to be exactly equal to, what would you have to have in here? The limit. Limit as h approaches 0 of this. Okay? That would be exactly what the f prime of a is. But as long as h is small enough, this is approximately that. It's exactly what we said in the last slide. Okay? That the slope, y2 minus y1 over x2 minus x1, which this minus this is just h. If that h is small enough, then that derivative is very, very close to that. Okay? If it's a continuous function and all the other things are met. Okay? So let's do example 6. Okay? Okay, they give us the table here, but let's look at it. Estimate the derivative of, change the silly color back again. Okay. F of x is equal to sine x. We're going to estimate that at x equal pi sixth. Okay? Now when you read that problem, what's one thing, especially if you're going to be doing some calculations here, what one thing should smack you in the face here about that? What mode should you be in? Radian mode for sure. In fact, most of the time that's going to be the safe. Unless you see degree sign popping up there, you always get to radian mode. If you just saw f of x equals sine x, just assume radian mode right at the beginning. Unless they said at x equals 15 degrees or something like that. Then you say, oh, oops, I'll be in degree mode. But if you don't see a degree sign anywhere in the problem, assume radian mode. Okay. Now, based on what we just said, how would you approach this? It says estimate the derivative. So we want what f prime of, well, actually, f prime of pi halves. I mean pi 6. That's what we're trying to estimate. The derivative at pi 6. Okay? Now, according to what we just did, how would you approach that? Back a slide or two. How would you approach it? I need to blow that up. What we're looking for was f prime of pi 6. What would we do here? We're looking for f prime of pi 6. So we would put f of pi 6 plus h minus f of pi 6 divided by h. Right? Now, okay, let's go back and write that somewhere here. Oh, I'm going back the wrong way. Sorry. Here we go. So that's going to be about f of, tell me, pi 6 plus h minus f of pi 6 over h. Okay. Now what's our f? Sine. So this will be sine of pi 6 plus h and what is sine of pi over 6? Ah, very good. 0.5. Save me some writing there. Over h. Okay? And that's what we're going to evaluate to see approximately what that derivative is. And then we're going to let the h's get very small. So where do you want to start the h to be? You can start it anywhere you want to. Does anyone just have a rough guess about what pi 6 is? No, just a number. Pi 6. Anyone know what pi is? 3.14. So it's a little bit greater than 3. Divided by 6 would be 3 divided by 6. Huh? 1/2. Exactly. Okay? So let's pick something less than 1/2, okay? Because why have an h that's bigger than what your pi 6 is? So let's call it 0.5. So let's make h point. I would have started at 0.1. They started at 0.01. That's a pretty small h. So let's do that one first. So what we're going to do is you get your handy dandy little calculator. Okay? Everybody got one, right? course, okay, and do, and however your syntax is on your calculator. I can't tell you what to enter in what order. My old scientific calculator, I have to enter the argument first and then do the thing. Most of the newer calculators, you do it just as you read it. So sine of, and then you're going to need to find the pi key, pi divided by 6. And by the way, the sign, when you do the sign, most of the time the parentheses opens up. So it's pi divided by 6, and then do plus 0.01. Close that parentheses, minus 0.5 divided by 0.01. Anyone get anything? Say again? Yeah, what mode are you in? What mode did you better be in? Radio mode. I hope everybody's there. What do you get when you do that calculation with 0.01? Ah, all right. 0.863511, blah, 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 right? Okay? You can write it down if you want to, but here it is right here. I don't think I can blow this up and not lose what's there. I'll try it. Let me try it. Oh, yes. Look at this. Just barely. Be a little easier to read then. Okay? Now plug in a 0.001. Sine of, and pi, open parentheses, pi over 6 plus 0.001 minus 0.5. Then hit an equal sign. I forgot to say that before. Did anyone get a bad answer before? Here's probably why. Whenever you have a numerator that has an addition or subtraction in it, be sure to either do an equal sign before you do your division, or do an open parentheses before you even start the sign, and then the sign opens parentheses, pi over divided by 6 plus h, close parentheses, minus 0.5, close that first parentheses, and then do your dividing by h, which is 0.001. Anyone get an answer there? What you get? Anybody? You get this? 0.86555775? Anyone who did not? Okay, good. Okay. Well, I'm pretty good about the 0.86. That looks like it's going to be good. Let's do 0.0001. Okay. Open parentheses, if you're going to do it that way. Open parentheses, sine of, and that should open its own parentheses, pi divided by 6 plus 0.0001, close parentheses, minus 0.5, close parentheses, divided by 0.0001. And what do you get? Anybody get it? Okay. 8660. So it looks like the 86s are still good. This was an 863. This is an 866 rounded up. So that 866 looks okay. Go another one. Open parentheses, sine of pi over 6 plus 0.00001. Close parentheses, minus 0.5. Close parentheses, divided by 0.00001. And anyone get that? Okay, so that looks good to 4 digits now. This one was good to 3. This one was good to 2, 3. This is good to at least 4. Okay. Maybe we'll stop on the positive side and start doing the minus side. This time it's going to be open parentheses, sine of pi divided by 6 minus 0.01, close parentheses, minus 0.5, close parentheses, divided by h. And you'll notice you get a number a little bit greater than these have been. In fact, that would be about 0.87. That's not far off, but it's not nearly what we have here. So try again. Open parentheses, sine of, that opens its own parentheses, pi divided by 6 plus minus 0.001, close parentheses, minus 0.5, close parentheses, divided by negative 0.001. Be sure I keep forgetting to say the minus, but be sure you do. And when you do, now we get something that's now down to the 0.866. Looks like 3 digits. That's better than we had before. We didn't even have 2 that time. 0.0001, well, we'll do open parentheses, sine of, that opens its own parentheses, pi divided by 6, minus 0.0001, close parentheses, minus 0.5, close parentheses, divided by negative 0.0001. And sure enough, we are now down to the same 3 digits we had before, and not quite the 4th digit yet. So we haven't improved it a great deal, but we have improved it some. And we finally try open parentheses, sine of pi divided by 6, opened its own parentheses, minus 0.00001, close parentheses, minus 0.5, close parentheses, divided by negative 0.00001, hit return, and now we've got 4 digits for sure, and close to being the 5th digit. Okay? Now, you know what I would do if I were trying to get a little more precision in it? Average these 2. And you're probably going to get even closer. Because these are increasing slightly as you go up. These are decreasing slightly as you come closer on that side. So my guess is going to be somewhere in between. So I would just throw in an average of those 2. Now, most of the time they don't do things like that, but if you wanted a little bit more precision, that's going to be close enough. Okay? Now, you want me to cheat a little bit and tell you what the real answer is? I don't think they do this in the book. So let me tell you. Okay? All right. We'll get to this later, so you can hang on to it now or you can forget about it and wait later. I will tell you f prime of x is equal to cosine x. So f prime of pi 6, I'm sorry, I was writing the wrong answer down. F prime of pi 6 is equal to cosine of pi 6. And since you got your calculators out, see what that is. Most of you might know it anyway. What is it? Anyone know that off the top of your head? Square root of 3 over 2. So you can either enter cosine of pi 6 or do square root of 3 over 2. I'd like some of you to do both of them just to see what you come up with. You better get the same answer. And what does that answer? Square root of 3 over 2 or cosine of pi 6. Second? No. Not right. Okay. Huh? Okay, 0.8660225. Second? 404. Okay, that's more precision than we got here. And what did I suggest that we do before? Average these 2 together, and that would give us 0.8660250. Not too shabby. That got us 6 significant digits there. We only had 4 here. Averaging the 2 got us up to 6. Okay? I could live with that. Okay? See how that works? Okay. Now, y'all don't know that. You didn't know that. I didn't tell you. Okay? So forget about it. Okay. There is a figure. There's a table. Here's the figure as we're doing that. Okay? Okay? Here's the sine curve. Here's pi 6, because this is pi halves. That would be a third of the way, pi halves. Okay? The sine of pi 6, when the h is less than 0, okay? In other words, you are the negatives, and coming in that way, your secant line is up here. They don't show you where that is, just slightly above that, and the closer you get, how close to the tangent line. When they just did a really strange one here. Way out here, that tangent line, that secant line here, as that gets smaller and smaller and smaller, is approaching the tangent line, slope of the tangent line. So you see going from both directions. And the tangent line is squeezed in between the secant lines when h is positive and h is negative. And that's why when I got them down really, really close, going an average of 2, that's going to give you pretty close to what that is in between. Now that's if it's a monotonic function. It's constantly increasing anywhere around that. You don't go up there and make a sudden bend. That probably won't give you a good result. But as long as it's monotonically increasing, not a bad choice. All right, any questions on that? Okay. Example 7 is not given in the slide set. There's no slide here, figure here, but it says determining, what did I erase what I just had? No, well, we'll use this. Okay, let f of x equal sine x. Show that the approximation f prime of x is approximately f prime of pi 6 is approximately 0.8660 is accurate to 4 decimal places. Okay? Well, they took the last entry on each column. They didn't round very well. If you took the last entry on the left-hand column, this was rounded to 0.866023. They in the book said 22, and this one would have been 0.866028. How did they do on that one? They rounded the second one right. The first one they didn't do a good job on. And anyway, you could just look at this and see. Actually, because you don't need the extra digits there, but the first 4 digits are the same. The 5th one is, except it would have been rounded up here, wasn't here, so therefore only the first 4. But if you average the 2 of those together, then you get even better, and that improved it up to 6 digits, because that was what we got with 6 digits. Okay. Now, conceptual insight. Are limits really necessary? Don't tell me you've put me through chapter 2 and now this much in 3 and now asking the question, do we really need these things anyway? It says it's natural to ask whether they're really necessary. The tangent line is easy to visualize. Is there a better way to do it? History gives one answer. The methods of calculus based on limits have stood the test of time and are used more widely today than ever before. Well, we've always done it that way. Isn't that what? you hear often. Okay. History aside, we can see why limits play such a crucial role. The slope can be computed, blah, blah, blah. So I'll let you read the rest of that. It doesn't seem like it. All that earth-shattering there, but I'll just let you read that yourself. They do have a summary here, quite, close to half a page of summary, so this covered a fair amount of ground here. And let me ask again, do y'all want to see preliminary questions or not in your text? Like to do those or not? I only saw one shake no shakes yes. Y'all want to do it? Anyone want to do those? We'll go with the one no. You rule the day. Nobody else answers. Okay, homework exercises then. Do any of the odds. Do number 1. Everybody should do number 1. Then do any of the odds 3 through 7. Either 9 or 11 or both. And that's referring to figure 12. So let you figure that out. Then do either 13 or 15. And that's referring to figure 13 in your text. Then do either 17 or 19. Then you choose any of the odds between 21 and 27. Do any of those. I would say more than one, but you choose. Then do any of the odds 29 to 45. Be sure to do some of those. 47 requires a figure, as does 49 or 51. Excuse me. So you choose any of the odds 47 to 51. And then any of the odds 53 to 57. And any of the odds 59 through 65. Some of those say you need a graphing utility. So if you don't have one, try it without it, but if you get stuck, don't waste too much time on it. Then do any of the odds 67 to 73. Then do 69. That depends on the table above it. And then do either 71 or 73. Now, if you they've introduced something here. One thing was Kirchhoff's law, which is a physics type thing, and if you do want to write on that as an application, you certainly can. Okay. A little bit prior to that, they say estimate derivatives using the symmetric difference quotient, which is, sorry about that, exactly what we were doing before. Okay. When I say once you get to the end, take an average. Okay. So I don't know if you'll find enough to do a paper topic on that, but that's what the SDQ was standing for the last several problems. Okay. Any questions? 3.1. All right, let's go on to 3.2. For some reason, PowerPoint takes so long to open. There, it's trying. For a while, it was just quivering, but now it's trying to open. Okay. Okay. 3.2 starts at the bottom of page 121. I'd almost lost it here because I flipped the page without realizing there was verbiage at the bottom. In fact, this equation's at the bottom of page 121. Now, the title here is the derivative as a function. I really haven't been treating the derivative as if it wasn't a function, except they were sort of isolating it a little bit. But remember, we would say what the derivative was, and then you plug in values. That's treating the derivative as a function, and truly it is a function. So this time, without having a fixed value here, we have the variable here. But it's done the same way. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. Same as before, except we had a's here, here, and here. This keeps it as a function. Okay? Now, just a couple of other things. Sometimes you'll see this written as, let me get my pen color back, okay, as y prime or y prime of x or f prime of x or f prime. I mean, they have all these things, and that's with just the primes, okay? Then they have dy dx, you know, and it just goes on and on and on. Different ways you can express them. They all mean the same thing, taking a derivative of some value x. And that's what we're doing when you're talking about derivative as a function. Okay? Now, I don't think, yeah, that may be the next slide, so let's go with this. The domain of f prime of x consists of all the values of x in the domain of f, in other words, that would have been f, for which the limit of equation 1 exists. So let's go back a moment here. Do you remember our function not long ago where it was going up like this and then down like that? Okay, we did one like that. Remember, I had to draw it. Okay, now, that function was defined everywhere. It looked like it was a continuous function, especially between x equals 0 and x equals 5. If you remember, it was drawn for that. Okay? Continuous function. The f was that derivative continuous everywhere? So it was only continuous from 0 to 3. Not counting 3. So when you start doing this, usually you assume f prime will be continuous everywhere f was, unless there's some place that derivative doesn't exist. So you have to watch out for those values. Okay? We say that f is differentiable. Okay? New word. Ugly writing. Okay? Is differentiable, which means you can take a derivative of it. Okay? On some interval a to b, if f prime exists for all the x's in that interval a to b. And notice when they say a to b, they write it this way, which means what? If they put parentheses around an interval, what does that mean? Say again? Okay. Except that the a and, okay. How would that differ from if I said that? This is just notation type stuff here. What's the difference between those two notations? Okay. I hoped I heard you say was, this one includes the endpoints. This is going from A to B, including the endpoints. This one does not necessarily include the endpoints. That's what this means. You include A and B. This one says everything to the left of A and to the right of B, but not A and B themselves. So that one we had before that went from 0 to, remember, like this, and then 3 went like that. The derivative, it was differentiable. From that graph, it looked like it would have counted 0, but would not have counted 3. Definitely not counted 3, because the function was not, the derivative was not defined at x equals 3. So you can put these all things. In general, we'll assume in the interval, but not necessarily the endpoints. They may be good on the endpoints, but we never can assume that. Okay? So that's what that notation means. Okay? So let's do example 1. Prove that f of x, which equals to x cubed minus 12x, is differentiable. Okay? I'm going to abbreviate like crazy. Okay? Now, what's required for it to be differentiable? Second?
Less than 0?
Not necessarily. It could be any value, but number one, this thing has to be continuous. Guess what? That's a polynomial function. Polynomial functions are continuous everywhere. Okay? So there's one issue. The second issue, and they haven't really harped on this much, but I think it's worth harping. It has to be smooth. So think jazz, really smooth. So, now I hope you remember this about polynomial functions. They are continuous everywhere, but they're also smooth. There are never any points or cusps or corners or other things, or discontinuities. They're continuous, but they're always smooth. Polynomial functions are. And if they are, that means the derivatives are defined in both directions everywhere. So that's what's required to say that it's differentiable. Okay. Now, then it says compute f prime of x. Now, someone tell me what the definition of f prime of x is. Not the approximate, the actual one. As in, look in the middle of the page here, folks. The limit, as h approaches 0, of, you can keep reading, f of x plus h minus f of x divided by h. Remember, we had two definitions. One was x approaching a, the other was h approaching 0. Remember that? Okay. Now, remember, this is simply a limit of your difference quotient, you can call it, or your slope. Change of y or change of x. Okay, that's exactly what that is. Nothing all that deep. Okay? But what we have to do before we can plug that in is go up here and figure out what f of x plus h is. Oh, big boo hiss here. What is that? F of x plus h. Someone tell me how to do it. Here's your f of x. What's the f of x plus h? Say again? X plus h cubed minus 12 times x plus h. Okay, I feel like a dentist pulling teeth here. Okay, now. All right. What is x plus h cubed? Does anyone know that off the top? And if you don't, do you know Pascal's triangle? Okay. There's a couple ways you can do that. Okay. One's sort of the brute force. Well, there's several ways. One thing you could do x plus h times x plus h times x plus h. That's why x plus h cubed is, right? And then you can square the first two and then multiply that by the other. That's the most straightforward brute force way of doing it, right? Now, does anyone know Pascal's triangle? It really is handy here. Okay, Pascal's triangle does something like this. You put a 1 up here. That's pretty easy, right? And then you put a 1 here and here. That's pretty easy, right? And then you put another 1 here and here, but to put in the middle, you add these two together, and that gives you a 2. Right? And then that's what you do. You put a 1 here and a 1 here, add these two together, and you get a 3, and add those two together, you get a 3. You can keep going doing this all day long. Make it as big and wide as you want to. I'm stopping there because guess what? This is x to the 0th power. Or it's a binomial, so let me correct that. X plus h. Why not? Okay. X plus h to the 0th power. Because what is anything to the 0th power? 1. Okay. How about x plus h to the 1st power? What's that? It's x plus h. It's the same thing. And look at the coefficients here. That coefficient is 1. This coefficient is x plus h. The coefficient is 1 and 1. Right? And does anyone know what x plus h squared is? Say again? Not quite. X plus h squared is x squared plus 2xh plus h squared. Look at the coefficients. 1, 2, 1. Right? Okay? This coefficient be 1, 1. This one just be 1. And guess what the next one represents? X plus h cubed. Okay? Can anyone write down for me what that is then? X, second, to the 3rd, plus x squared h. You drop the first one by 1 and increase the last one by 1. Okay? Next. Plus 3 x h squared, right? Plus h cubed. That's it. Now, go through. In fact, it's pretty easy to do. Take this and multiply it by that, okay? And see what you get. X times x. X squared times x will be x cubed. X squared times h is x squared h. But if you did 2xh times x, you get another 2, and that would give you 3x squared h. And then this one times that one. No. Yeah, we've already done that. Then this one times that one, we already did that. It's all. This one times that would be 2xh squared, and then this one times that would be another xh squared, so that gives you 3 of them, and then the last one would be h cubed. Yeah. So you could do those in either way you want to do it, but that's the first one. So let's write that in. This is equal to x cubed plus 3x squared h plus 3xh squared plus h cubed minus what? The line just above it. We've just done x plus h cubed minus 12 times. Just distribute, huh? 12x minus 12h. Got it. Okay. So that is just that first part here. So here's what our f prime of x is. The limit as h approaches 0 of, let's write all that out. This is so much fun, isn't it? This would be x cubed plus 3x squared h plus 3xh squared plus h cubed minus 12x minus 12h. Minus, what's your f of x? Here it is. X cubed minus 12x. And all this is over h, right? Okay. Now, how are y'all doing your subtractions? Are you okay? Do I have to write it all again, or can you just do the subtraction as we go? F prime of x is equal to the limit as h approaches 0 of, now here's an x cubed and here's a minus x cubed. Those add to 0, right? Okay. Can't do anything here, so this is going to be 3x squared h plus 3xh squared plus h cubed. Here's a minus 12x, and here's a minus 12x. Those add to 0, right? You don't believe me. We should have taken another step, shouldn't we? This would have been minus x squared plus 12x, and that plus 12x and the minus 12x wipe out, right? So they're gone, okay? And then we just have left a minus 12h. All this divided by h. Okay. I should have had y'all doing that. I was doing too much myself. What would you do next? Second? Plug in h equals 0. Then you'd be dividing by 0. Send your calculator crazy on it. What's that? Factor out an h in that numerator, okay? This will be the limit as h approaches 0. And in the numerator, every term has an h in it now. So factor 1 out. And what does that leave you with? 3x squared plus 3xh plus h squared minus 12 divided by h. Now what you want to do? Yeah, try it. They will divide out, absolutely, leaving you 1. Now you can plug in the h, okay? And what does this give you? As h approaches 0, what's that limit? 3x squared, because there's no h there. What does this one happen? It goes to 0, because h is 0. Multiply anything by 0, it disappears, right? And this one goes to 0, even faster, minus 12. So that appears to be f prime of x. Okay? So the second part says compute f prime of x. Okay? So we've done that. Everybody buy that? It was a lot of fun too, wasn't it? Oh yeah. Okay. All right. Now it says find an equation of the tangent line at x equal -3. So someone remind me what the equation of a tangent line is. How does that look? Anybody? Wasn't it something a lot like y minus y1 equal m times x minus x1? That's called the point slope formula, right? And when x is equal to negative 3 that's what we're asking for, the equation of the tangent line at x equal negative 3. What two things can you tell me about when x is equal to negative 3? Say again? Differential, yeah, well, we are going to do that. But one thing you can do, what happens if you plug in a negative 3 here? Since we're dealing with functions, let me rewrite this ever so slightly. Y minus f of x1 is equal to m times x minus x1. Isn't y1 f of x1? Okay. So if we're looking for the x equal negative 3, we know what x1 is. Negative 3. And what's your y1? F of negative 3. And that's pretty easy to do, isn't it? Maybe not at 8 o'clock on a Monday morning, but it's not that bad, is it? Can't we do that? Can I do it right down here? F of negative 3. Plug it in, plug it in. What do you get? Say again? 27. Negative 27, isn't it? Negative 27. There's more. Minus or plus? You're putting a minus 3 in. Huh? Say again? Plus 36. And what's that equal to? Minus 27 plus 36. Such high-level math this early on. Oh, that's 9. Okay. So f of negative 3 is equal to 9. That's your y1. If x is negative 3 is your x1, that's your y1. Right? Okay, we got part of it done. Now, what were you talking about differentials? You just threw out the word? Okay. Good throw out, but guess what else we can do? Now that we know what f prime is, and what is f prime, by the way? What's your first derivative? The blank of your blank blank. Say again? Okay. Isn't it the slope of your tangent line? And guess what the m is? It's the slope of the tangent line. That's the slope, right? So therefore, if we plug in your negative 3 here, you're going to get your m, aren't you? Okay? So let's do that. I'll rearrange it. F prime of negative 3 is equal to a little louder. $27 minus 12 is? Say again? 15. All right. Such high-level math this early on a Monday morning is terrible, isn't it? So this is your m. This is your y1, or f of x1, right? I think we can write down the equation of the tangent line, can't we? What will it be? Y minus 9 equals 15 x. Second, which is? Second, plus 3. your x1 was your negative 3, right? And minus and minus is plus. Okay, we can clean that up just a little bit. How? Y minus 9 is equal to 15x plus what? Oh boy, okay. 45, okay. And then what? Add 9 to both sides. Okay, so you get y is equal to 15x plus 54. Let's see how they did. Yes, they got it right. Good for them. Aren't you proud of them? Okay. Now, here it is. Here is the graph of that cubic function, x cubed minus 12x. By the way, looking at that, what can you tell me about that function? As in even or odd, or neither? Oh no, that was pre-calculus. We don't need that anymore, do we? Is what? Odd. It's an odd function. Both of the exponents are odd. It's easy to do with polynomials. Not so easy with other things. But this is an odd function. And sure, what does that mean? Okay, yeah, we got the exponents are all odd. But what does that mean about the graph of it? Of course we know that. No, it looks a little like it, but not quite. Sine is a trig function. This is a polynomial function. What difference does even and oddness make anyway?
Odd be a parameter.
Second?
Wouldn't odd be a parameter?
Odd be what?
A parameter.
No, parabolas are basically sort of evenish. Okay? What it means is if it's an odd function, it's symmetric about the origin. Whatever is happening here, the opposite is happening here. Whatever is happening here, the opposite is happening there. Whatever is happening here, the opposite is happening here. Odd. An even function is going to be symmetric about the y-axis. Whatever happens on one side, the same thing happens on the other. Not the opposite, but the same thing. And neither, you can't tell on the fingers. No, I mean, you can't tell anything about the graph. But an odd function is. And that sure enough looks like a good symmetric about the origin thing. Whatever is happening over here, the opposite is happening over there, right? That was not necessary, but we did it anyway. Now, notice their scale, okay? Bizarre but true. This is 2 on the x-axis. This is negative. This is 20 on the y-axis. So not exactly a 1-to-1 scale, but it's still evenly scaled. So it's you get the basic shape is symmetric and all like this. So the next thing we did, in fact, one of the first things we did, we plugged in here what x equal -3, and that gave us y is equal to 9. Remember we did that? Pulling teeth, remember? Okay? So that gave us a point on the graph. That's the one we're interested in, when x is equal to -3. That point right there, 9. Of course, if that's -3, this is 9, obviously the scale, but it's fine. Okay? And then we wanted the slope of the tangent line there, and this slope of the tangent line says you have a +15 slope. Well, that doesn't quite look like a +15 unless you realize +15 is like this and 1 is like that, So, yeah, that probably is a +15. And the y-intercept is 54. And this is 20, and that would be 40. Yeah, somewhere up there is 54. So that looks pretty reasonable. Right? Okay. Good deal. Okay, before we get to Godfrey Leibniz's pretty picture there, we're going to do example 2. Prove that y is equal to x to the minus 2 is differentiable, and then we're going to calculate y prime. Okay? So first we need to prove that it's differentiable. Now I'm not sure my proof is quite up to their standards. But what can you say about that function to begin with? Looking at it, studying it, pondering it, mulling it over, what can you tell me about it? Y is equal to x to the minus 2.
It's going to be smaller than x.
Say it one more time.
It's going to make x smaller.
Okay. Why do you want to do that? I mean, it's a fine thing to do, but what happens when x gets small and smaller and smaller? Another thing you can do, I don't know if this is helpful, what's another way to write that without a negative exponent? Say again? Let's not do that. 1 over x squared. All right, that's pre-calculus algebra. Who needs that? Okay. Isn't that what that means? When you want to get rid of a negative exponent, send it downstairs or upstairs 1, whichever it's not, and change the sign. That's what negative exponents do for you, right? We knew that, didn't we? Okay, don't bother. Okay, now looking at that form, what can you tell me about that function? Anything reach out there and slaps you in the face.
It gets closer to 0.
Say again?
It gets closer to 0.
What happens? Huh?
It's small.
Really? 0 gets smaller, but what happens to 1 over x squared? Okay, just take x equal 1. Huh? Okay. All right. You are wanting x to get close to 0, so let's get it. Yes. Okay. I'm not going to get real close to 0 yet, because I don't like 0 that much. So let's just x equal 1. What would that be? 1. Okay. Let's get a little closer to 0, like 1/10. Right? Closer to 0, right? Oh, how about negative 1? Let's do negative 1 on the other side. What does that become? 1. Okay. How about 1/10? Okay. What's 1/10 squared? I think 0.1. What 1 squared is? Say again? Okay. 0.1 times 0.1 is? Okay. How about algebra? Okay. 0.01, exactly. Okay? Now, if you're dividing by 0.01, which by the way is 100, right? If you're dividing 1 over 100, right? That would be 1 times 100 over 1, so that 1/10, x equal 1/10, this would be 100. You buy that? Do I need to write it out? Okay. 1 over 1 over 100. Right? Oh yeah, fractions, we love them, don't we? That's the same as 1 divided by 1 over 100, right? Which is the same as 1 times 100 over 1, which is 100, right? So you've gotten closer to 0 with your x, and what's your y happening? Okay, do 100th, and then it would be 10,000, okay? 1,000th would be 1,000,000, okay? I think it's getting out of hand, right?
So wouldn't like essentially be 0 to infinity?
What would be?
The equation for it would be 0, comma, infinity. 'Cause, like, this
Okay,
thing
you
goes to
mean
0.
the range of that?
Yeah.
Okay. The range of that would certainly be going to a positive infinity. The thing is, it'll never be 0 though. Because the only thing that would make this 0 is the 1 was 0. And 1 is never 0. So basically, this is a function. If we started this way, it would look like this. I don't draw too well, but that's what it is. Because guess what? An even function, right? And it's not a polynomial, but it is even. As x gets close to 0 from the negative side, x squared is positive, right? So that's where it's going. So it never reaches 0 for a range and goes to positive infinity for the range. Yeah, you're right. So now that you've gotten me to draw the graph for you, okay, what can you tell me about those functions? That function. It's defined for all values x greater than 0 or for all values less than 0, but it's not defined at x equals 0. By that? Well, it has no answer there. I mean, it gets larger and larger and larger. Anything close to 0, you can't get an answer. It may be huge, but you can't get an answer. But at 0, you can't. Can't ever divide by 0. Okay? So, this function is defined for all x's from negative infinity to 0, not counting 0. Remember parentheses? And it's defined from 0, parentheses, not counting 0, all the way to positive infinity. It's good everywhere except x equals 0. So therefore, since it's a continuous, smooth function everywhere except x equals 0, it is therefore differentiable everywhere except x equals 0. So it's differentiable everywhere on its domain. It's just that domain doesn't include 0. Okay. Prove that it's differentiable. The domain of this is all x's as long as x is not equal to 0. So we assume x not equal to 0. We compute f directly. So let's do that. Okay. I'm going to erase some of this if it's all right. Even my pretty picture, can I erase it too? Oh, we may want to keep that. Oh, I erased it anyway. Okay. We may draw it back, but whatever. Okay. You know, I'm beginning to regret. Let's put this back like this. Okay? Now, what's our definition for the derivative? It says calculate y prime. We showed it's differentiable everywhere it was defined. It's differentiable. How do we define this? What's the definition for y prime? The limit as h approaches 0 of f of minus f of x. Okay, I'm a little slow. Over h. That's it. So, what we've got to do first is that's y prime, so this could be y of x if you wanted to write it that way. We were writing f of x. So first we've got to figure out what, and we're saying this is equal to f of x. I used to tell my pre-calculus algebra class, remember this. If you remember this, you got most of pre-calculus algebra done. Y is equal to f of x. Okay, if you remember that, just about everything else will fall into place. Okay? May have to stretch it a little bit. So, what is your f of x plus h then? Someone help me. Say again? 1 over x plus h squared minus, I've left off the limit. We're going to go back and put that in a minute. 1 over x squared divided by h, right? Okay. Can we fiddle with that first denominator? Do we have to? Yeah, we do. Okay. So that's going to have to be 1 over what? X squared plus 2xh plus h squared minus, right? Now, what do we got to do with that numerator up there? Yeah, you got to have a common denominator. Any ideas what that might be? When all else fails, multiply them together, right? So let's do that. Common denominator is going to be x squared times x squared, blah, blah, blah. X squared times x squared plus 2xh plus h squared, right? Now, what did I have to do to the first one, what I had there before, to get that new denominator? I multiplied by x squared. So I have to multiply the numerator by x squared too. Notice how tricky I did that. Okay? What did I have to multiply the second one by? X squared plus 2xh plus h squared, right? Now we have a common denominator, don't we? Thank goodness, okay? So our first numerator is x squared minus, now let's distribute the minus sign into the numerator of the second one. What does that give us? Negative x squared minus 2xh minus h squared, all divided by x squared times x squared plus 2hx plus h squared. I didn't really want to multiply all those together, but I could have. It's just easier to write it that way. No, it's not. You could multiply them, whatever. Now, what do you notice happening in the numerator there? The x squareds add to 0, don't they? Okay? Oh, and this is all over h. I forgot that. Don't forget that. Okay? Now, what do you notice about that numerator, what's left of it? Okay, say that one more time. That first, the top numerator, what do you notice about it you could do? You came up with it before. Factor out of h, of course. Okay, so let's do that. In fact, just factor out an h. Okay, and what you're left with here is a minus 2x minus h, right? Now, this numerator, I'm going to go and write them out. I was trying to avoid it, but I don't guess there's any reason. X to the fourth minus plus 2hx cubed plus h squared x squared. I don't know if that's helpful or not or whatever. I don't care. Okay. Right? And that's over h. Guess what? Those can go. Right? With sound effect. Okay, okay. Now we're taking a limit as h approaches 0. And let's do that. What does that numerator become? Pretty exciting stuff, isn't it? As h goes to 0. What does that numerator become as h goes to 0? No. This goes to 0. I buy that. you're left with a negative 2x, don't you? That's all, folks, okay? And how about this denominator's gone, so it's a 1. So what does this one happen as h goes to 0? This goes to 0. That goes to 0. So you're left with x to the 4th. And then what's that? Minus 2 over cubed. Minus 2 is left up here. This one wipes one of those out, right? If nothing else, write that x forth as x times x times x times x. One of these cancels one of them out, and you're left with x. So let's rewrite that back like the original was, and that would be minus 2 x to the second? Negative 3. You got it. Whew. I feel like a dentist. Okay, now, so this is f prime of x. Minus 2 times x to the minus 3. Okay? And that's all it's had to do. Oh, this is also what we call y prime. Okay, sorry. Okay. Now, that limit again exists everywhere it did for the original, which is everywhere that x is less than 0 and everywhere x is greater than 0, but not at x equals 0. Yeah, you can plug any of those numbers in here. Perfectly fine. You just can't plug in at x equals 0. Not allowed. But that wasn't allowed in the original either. So the limit exists for all x not equal to 0. So x is differentiable, and that prime, that's what the derivative is. All right. That was fun, wasn't it? Oh, you're still writing. I'll let you write some more. Huh? But it's fun, right? Of course it is, yes. Okay. Now, anyone know who this is? And what difference he made? That was good old Gottfried Wilhelm von Leibniz, I think is how you pronounce it. Okay? What's he famous or infamous for? Okay. That was the big argument back in the late 1600s, early 1700s. Who invented calculus? Of course, the Brits believe Isaac Newton did. But Newton was an ornery old cuss, and he didn't want anyone to ever question anything he did. So he had to be absolutely certain that what he had was right before he would publish it. Now, what he did do was send out thoughts to other mathematicians and say, you know, what you think of this? Could this be, you know, I'm developing this, what do you think? You know, so he did sort of collaborate a little bit, and he had written some of his early stuff to Leibniz. Now, the question is, had Leibniz been working on this before, or did what Newton sent him start him thinking? Newton continued fiddling with it and messing with it and doing stuff for years. Leibniz went on and started and developed and published it first. And Newton blew his top, okay? I mean, he was so angry because he swore that Leibniz stole his stuff because he had sent him some things for him to review and discuss, and then Leibniz turned around and, as they say in the academia, he scooped him, okay? They use in literature, journalism also, that Leibniz rushed and got it published first. So that was a huge debate that went on just about the rest of their lives. Who did it first, you know? And Leibniz published it first, but Newton swore he came up with the idea first. Okay. Have y'all, I can't remember the name of the movie now, but it was based on Facebook, the development of Facebook. It was a movie that won an Academy Award, I think, for the actor in that, who was an unknown actor beforehand. Huh? Yeah. Who did? Huh? Yeah, exactly. What's that?
There was a debate about the McDonald's that too, wasn't it? That the original creator wasn't actually the original guy who made it.
Yeah. Well, guess what? Microsoft, Bill Gates, he stole the whole concept of doing things from somebody else. I mean, there's a lot of this that goes on, and usually they settle what, I can't think the guy who is credited and who owns Facebook now, but he bought off I think it was a couple of twins. They were all students at Harvard together, and they ran this idea past him, and he took it and ran with it and developed it before, because they weren't good programmers. He was. And so he developed it, and they were furious. Furious, but he's rich. They sued him for $1 million or two, but that was chunk change to him. He paid them off and hopes never to see him again, I guess. Okay, anyway. German philosopher, scientist, Newton and Leibniz, often regarded as the inventors of calculus, working independently, or at least now we just say they were. I don't know if they really were or not. It is more accurate to credit them with developing calculus into a general and fundamental discipline, because many particular results of calculus had been discovered previously by other mathematicians. So that's what Leibniz is known for. But what he's known even more for, Newton's notation for calculus was a little bizarre, okay? He didn't call it calculus, he called it fluxions, which meant movement, flux through things. Leibniz, broke it down into differential. I think Newton had too, but Leibniz's notation was just a lot cleaner. So we use Leibniz notation, even though we still say Newton developed it, So that's what we're talking about here. Wow. They sure skip a lot of slides. Okay, let's go back and do this. The prime notation was introduced by Lagrange, not Leibniz, not Newton. We've been using it all along, y prime, f prime of x. That was Lagrange, many years later, okay? I'm sorry, not that many years later. Well, yeah, he was born 20 years after Leibniz died, and so he lived another century past with Leibniz's death, okay? But this notation, df dx, or dy dx, that's not Leibniz, okay? Now, so in the last problem we did, we said y is equal to x to the minus 2. We say y prime is equal to minus 3x to the, minus 2x to the minus 3, right? If you wrote it in Leibniz notation, it would be dy dx is equal to minus 2x to the minus 3, okay? Now, another way you can say that is d of x to the minus 2 dx is equal to minus 2x to the minus 3. So you can, rather than putting the y up here, you can actually put that function of x up there. And you're doing the same thing. So lots of different ways to write the same thing. Okay? Now, whereas before we might say y prime at, give me a value, any number. 3? 2? What do you say? 3. Okay. That would be, you take the derivative and then evaluate it at 3, right? In Leibniz notation, you say df dx when x is equal to 3. Yeah, same type of thing. Okay? In the book they use 4. Whatever. Okay? Or dy dx when x equals 3. Or 4, whatever you want to plug in there. Okay? Now, what are these things called? Okay, sort of sorry, one left because we. Oh, by the way, does anyone need a bladder break? I'm guessing that may be where one went. I could use one. So you want to take a quick break? We don't have to be gone very. Okay, we started off with 10, didn't we? Did we lose somebody? Was someone sitting? Yeah, okay, she's coming back. Okay, that's her stuff. Okay. All right, I'll just talk about the different notations. This one's typically called not Leibniz notation, whether you put F or Y there. What are these called? That's about the time I noticed one was gone because I said I knew one was going to give the answer, but he wasn't here, so that's why we took a break so he could come back. These are called the differentials. This form is called the derivative. Separately, they're called differentials. Now, in reality, this is an operator, okay? So you really shouldn't be separating them, except they do sort of stand alone as well. So it gets to be a little fuzzy. And if you think about it, if you go back to the definition of our derivative, that's the limit as h approaches 0 of change of f or change of y over change of x, isn't it? That's what we were doing. We were doing the slope of a secant line and taking the limit as the h approaches 0, delta x approaches 0, and that's what gave us the slope of a tangent line. So in a sense, delta is actually a physical difference, 0.03 or something like that. D is the limit of that as this goes to 0. Okay? So the dy dx is the limit of your delta y over delta x as the delta x goes to 0. So I probably should change that. The h was your delta x, by the way. So let me go back to that notation. And to me, this makes Leibniz notation make a lot more sense. It's the delta is going to, as your limit, as the delta x goes to 0, it becomes a dx. And that represents that. However, this is really a division. This isn't. That's an operation. But that's what the operation's doing. It's got that limit included in it. Okay. So it says you should not think of dy dx as a fraction of dy divided by dx, even though it's the limit of a fraction, okay? The expression, the dy and dx are called differentials. They play a role in some situations, linear approximations and that kind of stuff. At this stage, they're merely symbols with no independent meaning. So why even bring it up? But they did. So here's a conceptual insight, okay? It's the limit of ratios. It's exactly what I just said. Okay. We'll see other advantages of Leibniz notation when we discuss chain rule. That's coming up later. Okay, now for some reason, the new book goes back to something we did earlier and calls Theorem 1 I'm not going to change it to red, but the new book's theorem 1 is the constant rule. D by dx of some constant c is what? Remember that? 0, you got it, okay? And theorem 2 was d by dx of x is equal to 1. Perfect, okay? Now, that even looks more like a fraction, doesn't it? If you said dx dx. If you ever see that, that's 1. It looks like a fraction. It's not. It's an operator, but you can still count on that being that. So with those two in place, okay, and you can go back and prove this by your limits and things like this, but it's really straightforward. We've already done it with the constant and with the linear functions. We just didn't do it with just the function x. We did it mx plus b and found it was m. Okay, but it goes, and this then is your theorem 3. In the new edition, this is theorem 3, the power rule. For all exponents in d by dx, and by the way, I never used to call it that, but I was tutoring an Indian student who were friends with their family, and he had studied and gotten his undergraduate in India in computer engineering or something like that, but he was needing to take, in India and Europe and most places you don't have lots of little tests and things like this. You take one big test at the end of your program of study and you pass or fail. I mean, that's it, you know. So he was doing his big test. Actually, it was given in like 3 or 4 parts, and his math part was coming up, and he was back home from India, and he needed tutoring in it. And I had never heard of it. You know, at least in my ears, Indians talk really fast. So it was DBDX. And I mean, that's how it sounded. I said, what did you say, DBDX? You know, and I finally realized D by dx, okay? So, and now I've gotten, so I say it, D by dx, okay? So if that's confusing to you. But d by dx, that's the derivative of this function, x to the n, is, let me blow it up for you here, even. And this is for any exponent n. That means n's don't have to be positive, they could be negative. It doesn't mean they have to be integers. They could be fractions. They could be decimals. Okay? The only thing we're not going to let them be right now are variables. Okay? But if they're any number in the world, this is true. Okay? And what you do is take the exponent, multiply it by the function, but drop the exponent by 1. That's the power rule. Okay? Now, got it? Now, I want you to do something for me. D by dx of x to the minus 2. Negative 2, x to the negative 3. Right? Oh, you went the wrong way, huh? Okay. Yeah, you're subtracting 1 from whatever this was. It was a negative 2, subtract 1 from it, and it becomes a negative 3. Does that look at all familiar? Didn't you like doing the limits better? Weren't they more fun? This is just so easy. It's just pathetic, isn't it? Remember our last example we did? That's exactly what we got. Right? I'll come back to something else later. Okay. So anyway, that's your theorem 2. That's the power rule. Now they do a proof of it, and they go through, and it's long, a little on the tedious side, and it has you do a generalization to begin with, which is indeed true, but I had never seen it done past x to the third, but indeed any x to the fourth and on up, the first factorization of that would be x minus a. So you have to take their word for that and then go on from there, but sure enough, that comes up to be true. Okay? Now, they like to say it in words, and I don't know that the words... Okay, this is part of their proof. If you ever have, and again, this is not something I necessarily would have thought of before, but it is indeed true. In fact, no, it's not even the same. It looks a little bit like the Pascal triangle binomial theorem, but it's not the same. But anytime you have x to the n minus a to the n, this can be factored as x minus a times, and then these are the rules you go through for all the rest of them. And that's the part that's a lot. You drop this by 1, okay, because this into that would be x to the n minus 1. And then the next term, drop it again by 1 and raise this by 1, okay? And then drop this by another and raise that by another and keep on going until the x is just a 1 here, n minus whatever is going to be 1. And this will be n minus 2. And if you'll notice, if this was n to start with, it starts out 1 less than n, 2 less than n, but this is only 1 more than, this is only a 1 here, but this is minus 2. So it goes on down until you get to that. So it's kind of symmetric, but to really prove this would be horrendous. They just say, this is true. And it is. Proving it, though, is a real pain in the neck. I think I asked this before. Are any of you math majors? Huh? No. Okay. You're all pre-engineering or something like that? You probably aren't as concerned with the proofs either. Okay. I wasn't a math major either. Okay. So, then that meant you could divide both sides by this, by that x minus a, and that would leave you in terms like this. And as long as x is not equal to a, of course, if x is equal to a, you wouldn't be dividing by 0, right? But if x is equal to a, then that doesn't make any sense anyway. That's 0. So don't do it when x is equal to a. So that's probably put that in there. And that's part of the proof, and it's an essential part of the proof. But man, what a pain in the neck. But this is what they were saying, writing that power rule in words. I'm sure not going to do this, but I can think it, okay? If you're raising a variable to any exponent, any numerical exponent, the derivative of that variable raised to that exponent is the exponent out front, that variable raised to 1 less power than the exponent was. Always a minus 1 side. To me, that says nothing better than n, but the book likes it, so they did it. If that helps you, go for it. Okay. Now, and again, I kept emphasizing, and they say this on the top of page 125, it only works when the exponent is a number. Any number will be fine, but only when it's a number. It can't be a variable. It can't have a variable in it. It doesn't work there. It's not a power function anymore. Okay? So let's do a few. Okay? Let me just make sure what the next slide is. Okay. Okay. d by dx, okay, of x to the minus 3/5. What would that be? Negative 3/5. X. Negative 8/5. Does everybody see that? You're subtracting, you bring this in front, like that, and then you write your variable here, and then subtract 1 from this. Subtracting 1 from 3/5, I subtract 5/5 from 3/5, and that's how I get a negative 8/5. Oh, 5/5. Okay? That's exactly right. Now, you could see that written in other ways, and don't let it confuse you. This would be a negative 3/5x to the 8/5. Is that the same? Why not?
Is on the first one, the powers over all of them compared to over here.
The power is only on the x, not on this. That's the coefficient. Then it would be the same. Yeah. Got to have the minus sign still there, and that minus sign could be out here rather than up top. So you can see it written different ways. Now, this would have been good for here or here. What does this mean anyway? Something to the 8/5 power. Multiplying the number by 8 and dividing by 5, is that what you said? Not quite, okay? This is an exponent. This is x to the 8. That's what the numerator is what exponent that is. What is that denominator, right? What undoes an exponent? A root. This would be the 5th root of x to the 8. That's what that means. This would be 1 over it. See, yeah, you could say it's the 5th root of x to the minus third. You could say it that way. Or several others, but here's one way you could write that. The 5th root of x to the 8th. So that's just one way. The other way, that's exactly the same as the 5th root of x raised to the 8th. So you can either raise the variable to the 8th before you take the 5th root, or you can take the 5th root of it, and then once you have that, then raise that to the 8th. Those are exactly equivalent. You can either have the exponent 8 inside the radical or outside the radical. Okay? Just a little bit of review of that good old pre-calculus, right? Just to remind you what those are. So these can be written other ways. All right. Beat that one into the ground. Let's do this one. D by dx of x to the square root of 2. Can you do that? Say again? The square root of 2 times x, the square root of 2 minus 1. Okay. Now be careful when you're doing this. As you notice, I'm not the neatest person in the world. I thought I was here at Bronx Cheerful today. Okay. So be careful when you write this that you close off your radical. That's why I dropped the little line here. This square root of 2 does not encompass the x. It ends right there. The square root symbol just is over 2. And up here, it doesn't include the minus 1. It ends at the 2, then subtract 1 from it. Okay? So square root of 2 is approximately 1.414. So this would be approximately x to the 0.414. You subtract 1 from it. But that's an approximation. That's an exact term. So yeah, anytime it's a number, it just can't have a variable in it. Rational, irrational. Now, we're not going to get into complex numbers, though they still work, but the rules are a bit bizarre, so we won't get into that. Okay? Now, we're so used, what's your favorite variable of all times? x. Everybody loves x. They don't have to be x's. What if you had d by dz of z squared? What would that be? 2z. That one was easy, wasn't it? And again, be careful with sloppiness. As you see, I slash z's so I don't confuse them with 2's. Okay, so do whatever you want to do, but when you see me writing a slash in it, that means it's a z, so you don't get it confused with the 2. How about this? D by dx, I'm sorry, d by dt, which sometimes they look a lot alike, of 20t, no, t to the 20th. What would that be? 20 t to the 19th power. Exactly. Very good. Okay. How about this one? D by dr of r to the 1/2. 1/2 r to the negative 1/2. Okay? Can you write that without a negative exponent? Okay? Very good. And without a fractional exponent, that would be 1 over 2 root r. I don't like that form, but all those are equivalent. Very good. This is, to me, the handiest form to do. Which, by the way, if you ever have a variable, especially written as a radical, change it to a fractional form. Okay? Before you do a derivative, because the power rule works with numbers, it doesn't work with radicals. I mean, it does, but you have to remember what they stand for. Okay. Now, the one thing that I was saying before, remember this only works when your exponent is a number. For instance, y is equal to 2 to the x. Is that a power rule function? No, it isn't. Because that's the variable as an exponent. That's a exponential function. They have a whole different set of rules. Okay? So don't try to use a power rule on an exponential function. Okay, next we come to the linearity rules. And in the old edition, this is theorem 2. In this edition, it's theorem 4. Okay? Here are the linearity rules. And by the way, you're not going to run into this in this course any, but if you continue and do any other upper level math courses, you will run into the concept of linearity in lots of ways. Assume that f and g are both differentiable functions. Okay? Each of those are differentiable. Then, this is always true. F plus g, the sum of those two functions, is a new function, but it's also differentiable. F minus g, the difference of those two functions, is a new function. It's also differentiable. And we know what the derivatives are. The derivative of that new function, f plus g, so f plus g prime is f prime plus g. So the act of taking a derivative over a linear combination is just or here's a better way, easy way to say it. Derivative of a sum is the sum of its derivatives. Okay? The derivative of the difference is the difference of those derivatives. That's linearization, or that's part of it. The other is the constant multiple rule. And this goes for lots of applications are linear, and you use this a lot, especially if you take linear algebra, which some of you may wind up taking. I think you might. So what would that be? If you have any constant c, not a variable, constant c, then c times some differentiable function is also differentiable, and what's more, the derivative of CF is c times the derivative of f. So the derivative of a constant times a function is the constant times the derivative of that function. Now they seem very straightforward. They seem almost intuitively obvious, maybe, to you, but they're extremely handy to use, and we use them all the time. Now they go through the formal definition of it, and it's not it's fairly simple. You do some tricks of the trade, you shift terms around a little bit, and you see that it does prove. I encourage you to look at the proof, even though if you don't like proofs, you give it a shot. Okay. And they just say the difference in constant multiple are proved similarly, so they leave that to you. Let's look at example 3. Okay. Find the points on the graph of f of t is equal to t cubed minus 12t plus 4. This looks an awful lot like example 1, but not quite. Two minor differences, but whatever. Okay. It says find the points on that graph. Now, am I requiring you to graph it? No, the book does graph it, but guess what? This is the beauty of calculus. It can do the work for you, and you don't ever have to graph it, because even if you did graph it, you'd still be guessing. Okay? So find the points on that graph where the tangent line is horizontal. Where tangent line horizontal. Okay? Now, what does it mean for a tangent line to be horizontal? Any line to be horizontal. What do you know about it? The slope is 0. And what's the slope of a function? The slope of a tangent line of a function. Oh boy, all this time. The slope of a tangent line of a function is its first derivative. Absolutely. Now, I hope no one gets offended at this, but some classes seem to like it. I don't know, number one, if any of you go to church or not, but I've been to several different churches, and they like to have children's church, especially for the big service, okay? And that's where all the kids go up for it, and then some adult, the pastor or somebody else, starts talking with them, and they always ask them quite often we ask them some question to get them engaged and stuff. And quite often the kids don't want to answer, and they're scared to answer and stuff. But there's always one little kid in the back. It seems like most of the time it's a boy. And if the silence goes on long enough, he'll say, Jesus, because he knows that most parents think the answer to everything is Jesus, right? Yeah, so why not, So when I say, what do you think you're going to do in this class? Take a derivative? That's going to be a pretty good guess, okay? It may not be right every time, but it's going to be a pretty good guess. So, never mind. That's silly, dumb. Okay. So, what is the slope of a tangent line? The derivative, the first derivative. Okay, you got it. Okay. Now, so guess what we might want to do? If we know that the tangent line is horizontal, that means the slope is 0. So for this to be horizontal, that implies that, right? And that implies what else? The first derivative of f with respect to, and by the way, if you haven't caught on to this yet, let me back off and say this. They talked around it and stuff, but they never actually came out and said it. Notice this is your independent variable. Whatever is in your parentheses is your independent variable. Give me a t, I'll tell you what f is, right? That means t is independent, f depends on t. Okay? Now this could be a y, it could be anything else, it doesn't matter. But that is the dependent part, this is the independent part. So when you do your derivatives, it's d of dependent by d of independent. Always the independent variable is in the denominator. That's what you're taking the derivative with respect to. So this implies that, that implies this. So guess what we got to do to the function here? Take a derivative, very good, okay? So f prime of t is equal to what? Now y'all want to do a limit? I know you do. Y'all love limits. What's the easier way? 3t squared. Now, here's something they didn't tell you. Yes, they did. Down here. If you got a constant times something, just pull the constant on the outside. Minus 12. What's your exponent here? Say again? 1. Okay, 1 times 12 minus 12 is still minus 12, right? And then what is that when you subtract 1 from 1? T to the 0th is? No, 1. Anything to the 0th power is 1, always, okay? So there's your derivative. Guess what? That 4 didn't come into the picture because this is 4 times t to the 0th power, right? So t to the 0 is 1. 4 times 1, that gives you 4, right? 0 times 4 is 0, okay? Don't even go there. It's just 0. A constant, oh, we knew that from before. Derivative of a constant is 0, okay? Several ways you can get there. Here's your derivative, okay? And what do we want it to be? Zero. So set it equal to 0. Solve that equation. How would we do that? No, algebra? We have to do algebra and calculus? No. We're through with algebra, aren't we? No, we're not. Okay. Say again? Okay, you certainly can do that, and I'm going to, because you said it, I'll do it that way. Okay, add 12 to both sides, and then what? 3t squared, that adds to 0, is equal to 12. Second, divide by 3. Okay, y'all are telling me this, so I'll do it. And that gives you t squared is equal to 4. And that means, say again? T is equal what? 2. I was afraid you were going to say that. That's the problem with doing it this way. You miss half your answers. Sometimes. Say again? Plus or minus 2. Okay? Now, yeah, oh yeah, we knew that from algebra, didn't we, Jacques? Here's what would have happened. Now, anytime you have, if this was a linear function here, proceeding that way is exactly the way to go. But anytime the exponent is greater than 1, as in 2, 3, or higher, then I suggest, now here's the other dumb question. I can't remember if I've done this one. In this class, when I ask what's the F word, what do you tell me? Factor. Very good. You better say factor. Okay. All right. Now that's true on many levels, isn't it? Okay. So what we should do here is 3t squared minus 12 equals 0. Since this is a quadratic, greater than 1 is your exponent there. What should we do first? Factor. And what would you factor first? 3, and that leaves you t squared minus 4 equals 0. Have you finished factoring? What can you factor further? 3. Say again? t plus 2 times t minus 2, and that's equal to 0. Okay? Now, you got three factors there. Anytime you have a series of things factored together, multiplied together, and the answer is 0, what does that tell you about one of those factors? Something's got to be 0, right? Now, can 3 ever be 0? Not in this universe, so that one's out, okay? Other thing you could have done was divided out 3's and you've been fine. But then you are left with either t plus 2 is equal to 0, or, y'all remember this, don't you? Please say yes, okay? Or t minus 2 is equal to 0. And what does the first one give you? Aha, t is equal to minus 2, or t is equal to plus 2. Okay, that's why you don't miss half your answers. Whereas this way, if you don't forget to put the plus or minus, anytime you take the square root of both sides of the equation, you got to put a plus or minus with the number. Okay, but if you forget that, and especially with 4, t squared is 4, t is equal to 2, of course. No, it's plus or minus 2. Okay, enough of that. All right, so those are two places where we think we're going to have horizontal tangent lines, right? Well, let's plug it in, plug it in. It says find the points on the graph where the tangent line is horizontal. Find the points. How do we list or name points? We don't do them Fred or Susan or something like that. No, we don't name them that way. How do we name points? Say again? Yes, ordered pairs. So we've got what t is. What we don't have is what f is, or the independent variable, or dependent variable. So how do we get that? All right, just like Glade, plug it in, right? Okay, so f of minus 2 is equal to what? A little louder. Say again? Oh, you've already done it. It's a minus 8, right? Plus 12 plus 4. Is that right? And that would be, I don't think that quite gets up to 20, does it? You probably did plus 2. That gives you 8, isn't it? Am I doing something wrong? I think that's right. Okay. And then let's do f of 2. What would it be? Okay, that would be an 8. 2 cubed is 8. Minus 24 plus 4. And that, I'm pretty sure, will give you, what do you say? Minus 12? Okay, that looks right to me. So did I do the first one right? When x is plus 2, you're at minus 12. Oh, I did do something wrong, didn't I? Oh, I didn't multiply by 2. This is a 24 here. Y'all should catch me on this kind of stuff. Don't let me get too far down the road making stupid mistakes. That would be 24. Because it's a minus 2 times minus 12. Okay. And then that, sure enough, is 20. You're right. Okay. 20. So there's your 2 points where you have, find the points on the graph where the tangent line is horizontal. The first point is negative 2, 20. And the second point is 2, negative 12. Without ever drawing the graph. Thank you, calculus. Took all the work out for us. Not too bad, huh? 2, negative 12, and negative 2, 20. All right. Here's the graph that shows that. Okay. Now, they did graph it for us, okay? Now, this function here, even, odd, or neither? Odd, even, so neither. Most functions are going to wind up, polynomial functions will be neither most of the time, except for those rare circumstances like the last one. That was a zero, that wasn't. You have a question or just stretch? Oh, okay. All right, the tangent lines at t is equal plus 2 and minus 2 are both horizontal, meaning the slope is 0. That's what I asked for, and then you plug those values into here and get what the order pairs are. Good deal. Make sense? Okay. That was example 3. Okay. Okay. I don't think we have an example for anything here, so we'll do it on the same slide. It just has nothing to do with that. Calculate, oh, here's that terminology again, dg dt evaluated at t equal 1, where g of t is equal to t to the minus 3 plus 2 times the square root of t minus t to the minus 4/5. Boy, I woke up this morning hoping we were going to get to this problem, didn't you? I'm just kidding. Okay, go for it. Okay. What would you do first? Y'all forgotten what my questions were. Take a derivative. Very good. Okay. And what happens if you do? Now, actually, in this case, I want to do something else first. What did I tell you I did not like to have in a function when I'm needing to take a derivative? Say again? Okay, no, I don't mind those. Radicals, exactly. I don't want to have radical in there because I don't know what to do with it. I do know what to do with it, but it's a pain in the neck or some other body part. Okay, g of t is equal to, so rewrite this. T to minus 3 is perfectly fine. I'd rather have it that way than 1 over t cubed. Okay, that's exactly like I want it. Next, as a negative x on it, by the way, plus 2 t to the 1/2 power. Perfect. Okay, how about the next one? Minus, don't take the derivative yet. We're not doing it. We're just rewriting it now. Leave it alone. It's fine like it is. Minus 4/5. Okay. Now we've got radicals into exponents. Now I want to take a derivative. So I said it wouldn't always be the right answer, but it was close. Help me. A little louder. Negative 3 t to the negative 4. Excellent so far. Next. Plus. Okay. What do you do with the 1/2? Okay, you multiply it by the coefficient. So that would be 1/2 times 2 is 1. There's more. Second, t to the negative 1/2 power. Excellent. Next. Plus, I like it, 4 over 5. T, negative 9/5. Fantastic. Okay? Except that's just dg dt. What we want is that evaluated at 1. I'd swapped notations on you. I should have done dg dt, but I didn't. You want me to go back to that now or keep it in the notation I started with? Huh?
We're good.
Huh?
We're good.
Okay, let's do g prime of 1, where t is equal to 1. And what would that be? Negative 3, because 1 over 1 to the 4th power is? I didn't know it would be that hard. 1, okay, exactly. Right? Okay. Plus 1 plus 4/5. If there's anything that I enjoy plugging in more than t is equal to 1, it would be t is equal to 0, okay? T is equal to 1 is so easy, you just wind up with your coefficients. But we don't quite have an answer yet. What does this lead to? Say again? Oh, okay. I thought you were talking to me. Well, minus 3 plus 1 is negative 2 plus 4/5. So I want to rewrite negative 2 in terms of fifths. How much? Negative 10/5 plus 4/5 is negative 6/5. All right. Playing dentist again. Okay. Yes, that's what they got. Good for them. Oh, no. How could it be? We've run out of time. Just when we're beginning. Well, we're always having fun, aren't we? Okay. So we'll start next time with derivative and behavior of a graph. Okay? Well, some of these graphs do tend to misbehave sometimes, so we have to watch out for that. And homework exercises here. You can do any of the odds 1 through 5. This is on page 132. Any of the odds 7 through 13. Either 15 or 17. Definitely do 19. It has 3 parts. Oh, wait. No. Stop at 17. We haven't done the rest of those. Okay, we'll pick up the rest of those later. Good deal. Any questions? Are y'all proceeding on the test? Okay, so far? Okay, good deal. And everybody did get one. I've asked that, I think, 3 times now. Okay, so just couldn't remember if everyone was there. Good deal. We'll see you on Wednesday. Hey! Yay! We get class 2 days this week. Isn't that nice? Okay.